Minglinag from G, and it's my really privilege to be back and to the new civil engineering building. I wasn't know, and I went to the main site because I haven't been in Cambridge for a while since the COVID, and then came to this brand new building and this nice seminar. I'm really privileged and happy to be here. So the topic today, I'm covering some of the works I have been done with the Tunji group, and we're doing mainly doing tunneling and do a lot of computer vision stuff and try to automate the process of tunneling safety assessment and doing the defect infections. So
I need to click on the slides.
okay, now it works. Okay, so for those of you who haven't been to Shanghai, I would like to invite you all to go. It's about a 12-hour flight, and well, direct flight. If not, then maybe take another extra few hours. And we have a nice campus. This is the main campus in city, not far from city center, about 20 minutes. We have a tube station just in front of the gate of the main campus called Tongji Station. And we have the Civil Engineering College and the Geotech department. And we also have a centrifuge just down opposite the main building. And yeah, you can see it's a quite nice campus. And we just passed the cherry blossom season about a month ago. So if you have a chance, you should go around the end of March or early April. And we have nice gardens, and this is a library. That's a front gate. Just to give you a flavor, you should visit at some point. I think it would be nice to introduce my background and to let you know a little bit about myself. So as Brian introduced, I did most of my study in Cambridge. I did the BA in Keys, and I was from college, gone with the Keys. And then I did a computer vision with Kenichi for my MH project, and the PhD was funded by a Japanese company called JogMag on the methane hydrate production, and I did the multi-physics simulation. Then I went on to the company called Mo Solutions, which specializes in underground logistics. Back then, Professor Robert Mayer was a really good friend of the company, and he's really supportive on this idea of putting all the logistics into the underground pipelines. And then I decided to move back to Shanghai and join the tunneling group, and I did a postdoc with the group. Then I stayed in Tunji Civil Engineering College to do as a faculty. So that's my brief background. And for my topic today, I think for those of you who have been working with tunneling or not, for tunneling, especially in the cities, we often would face this type of disturbance or excavations. You always want to build some buildings nearby or do some excavation or a new tunnel. So that's a typical Shanghai. I'm sure that happens in London at some times or not, but not that as often as Shanghai. But surely every mega city faces this type of problem. And as an aging infrastructure, in the tunnel, you always face those type of defects, say crack, spalling, leakage. And if it's a segmental shell tunnel, then you have dislocations and typical deformations. Back days when I did the MH project with Kenichi, we do manual inspection. So you go down the tunnel at midnight and you use your glowing eye, try to identify the cracks or leakages, and you take some total station measurement if you do have them. But nowadays, for the last decade or so, a lot of researchers has advanced the technology to do vision-based use, either cameras or laser scanners. And there are two typical approaches. You either take 2D images and try to identify where the cracks or the defects, and then also lately a lot of focus was on the 3D inspection, try to obtain the whole picture and the location of the defects. And then for the defect inspection in Tungji, we used the list of the top spec ZNF profiler. It's a German company, and we built this small EV, try to carry that profiler's leather scanner to get the cross sections of all the tunnel linings and obtain the point cloud data. So this is very efficient, and you can get the really nice amount of data from the shell tunnel. And based on the data, you can do data analysis about the deformation, because it's a profiler to get each cross section, and each minute give you about 1 million points. So from that amount of data, you will be able to do analysis on the deformation. So for typical shell tunnel, we usually make some assumptions of the possible shape. So ellipse is always the logical one to go first. And if you do some surface fitting and some of the point cloud denoising, you will be able to get a pretty good shape of the shell tunnel. And then you will be able to calculate the convergence of the tunnels, and then also you can extract the segment next to each other, try to work out the dislocations. And that's for the deformation part. And then if we move on to some of the surface defect, as a leakage is an example. As a point cloud, one of the good things is you can invert the point cloud data into the 2D and the grayscale image, because the point cloud or the leather scanner is essentially the intensity or reflectivity of the surface. So you can convert that into the grayscale image and use the typical image analysis, or nowadays we use a lot of deep learning algorithms try to extract your target object. Here we specifically used the Mars Gaussian. That was about 5 years ago, was proposed by Google. Then we used this specific algorithm, but we upgraded it to the specific task for the leakage detection. And with that, indifferent to the typical image segmentation tasks, because we know the sense of the location of the leakage, or because the leather scanner gives you the location of each point, you will be able to calculate the leakage area as well as the location of the leakage. So you will be able, from that whole process, be able to tell exactly the leakage area and where the leakage is located at your cross section, which segments. So with that, you will be able to generate a report of the leakages. Another typical problem for the tunnel is the spalling. And spalling is, in fact, a 3D defect. But most of the time, if you only take an image, you will treat it as a 2D. But if you treat it as a 2D, you would not be able to, first of all, you would not be able to get really good segmentation results. And the second, you will not be able to extract the volume of the spalling. So you will not be able to provide the operational company of the metro tunnel, say, what strategies of your maintenance for that spalling defect. So to address this issue, we proposed a new network called StreamNet. So the idea is basically combining the intensity image or the grayscale image from the point cloud together with the depth image. Because the leather scanner can give you the dimension in XYZ, so you will be able to, I'm sorry, that's. Yeah, so from that, you will be able to convert your data in that direction to a depth image. With that, for each spalling defect, you will be able to have one intensity image as well as a depth image. Then we created this specific network, try to combine the depth image and the intensity image, and fusion the prediction results to give you a better sense where the spalling defect is. And with that, you will be able to calculate the 3D volume of that specific spalling defect. And also as we compared with some of the state-of-the-art deep learning or the image processing techniques, we have a better results. And another one, I'm not sure the specification in the UK, but in China, in order to inspect the tunnel, we also focus on the cracks. And the cracks in Chinese code, it's you need to be able to tell if there is a 0.2 millimeter crack. If there's a larger crack than 0.2 millimeters, you should inform the operation company to do something. So that's quite challenging. And for the laser scanner, the resolution usually around the 1 millimeter. Even the one we use, the state-of-the-art one, it's about 0.5 to 1 millimeter. That's a maximum resolution you could reach. That's why a lot of the focus was done on the linear camera system. The advantage of this system is it's very efficient, and it can, because of the strong illumination and the high resolution of the linear scan camera, it can give you a really high spec of the images. As you can see, we did a few tests in the tunnel. It can give you about 0.1 to 0.2 millimeter resolution. And that's a really high resolution, which really need the high spec cameras and high align illumination of the linear lights, and also the control of everything together. And with that image we acquired, we we proposed the PNet plus A-star algorithm. For most of the algorithms or the guys doing computer vision, a lot of them have done crack detection, and it's a classical problem for any concrete structure or geotech structure. But the problem for most of the crack detection algorithm, they have crack disjoints, because crack is such a fine detail object. It's in comparison to the leakage and spalling, it's very difficult to detect, and usually there's a disjoints between the cracks. And because, as I mentioned, the accuracy of the crack to detect in the regulation, you needed to have really good continuous crack to be able to quantify later on. That's why we proposed the PNet to fuse a different part of the outcome of the image, try to extract the fine detail of the cracks. And in order to really get the correct quantified crack width and the length to be accurate, we use this searching algorithm called A-star. Most of the crack quantification, they use the middle axis approach. So if you identify a crack, for example, and you will just use the middle axis. So you assume if it's a 2 millimeter crack, you just try to take the middle axis and calculate the length. But that sometimes leads you to about 10% error if you do that simple approach. That's why we try to use this A-star algorithm to give you a better crack performance, detection performance. So if you compare our algorithm to some of the other state-of-the-art ones, you can see some of the immediate improvements as well as the quantification. So we call it a skeletonization to get a better accuracy of the cracks. That's a defect part. So towards the future, we have the concept of combining the laser scan and the linear cameras. So those are the prototype model we are on the building for the track and also for the highway tunnels. So by combining those two, we think we should be able to capture most of the information we require for both the deformation, the surface defects, and the fine crack defects. And with that information, all you got, the target usually is you needed to tell your clients whether my tunnel is good enough, is it safe or not, should I do something? And to do the tunnel lining safety assessment, most of the approach we do nowadays is I showed you, you take a lot of images and point cloud data at night, and you process it for the next week or so. Then you give the client a report.
but that's not good enough for sometimes you want to have real-time results to show your client that the client can go at the cloud or at the desktop to see if there's any problem. So for this, we try to combine the inspection technique together with the monitoring technique. So we implemented some of the lasers, tilt and sensor node at the tunnel lining, and these sensor node can talk to the inspection equipment. So the inspection equipment together with the monitoring equipment combined become a mesh network. With that, you will be able to create a system which can not only monitoring, but you can also give the inspection results together as a network. So this guy, I think he is quite closely associated with CSIC. He's one of the early doctors who worked with Kenichi, did the mesh nets and wireless sensor now. So we work with him as well. He's now based in a city near Shanghai. So we worked with him, implemented those sensor node in the tunnel. And with this sensor node, you will be able to adjust your frequency to get the distance. So it's essentially the convergence and also tilt, which is the rotation of your structure. And with that, you can consider our inspection equipment is one of the sensor nodes. So with that mesh network, you will be able to collect the data from both the monitoring and the inspection through the gateway and to the cloud to process it. And this is one of the concepts we try to show is when imagine, although this laptop is on the EV, if imagine that laptop is sitting in your office, you will be able to see during the inspection what the defect looks like and the key defect information. So from there, essentially, whoever doing operation down tunnel and the management level can see at their office. And with that, we also say that in order to process that data on site, you needed to introduce some of the edge computing idea. Essentially, you needed to streamline all the data in order to allow the on-site, either a small desktop or edge computing processes to process. So you needed to define what defect data you want, what data structure is, and you also need to allow some of the monitoring data to be processed before presented to those who is concerned what sort of strategy to maintain the tunnel. So those should be done at the site to give a nice data structure to present at the desktop. And with all the defects and the data structure organized, when you try to assess the tunnel, how good it is, it's a multi-aspect, right? So that's sort of the indexes we try to propose. We look at both transverse and longitudinal deformation information you obtained from the laser scanner. And also together with some of the defects, surface defects I showed you through the computer vision technique, like the cracks and leakage. For here, we both consider the typical geometries, Eulerian, the length or the width. Also, we took into the fractal numbers to looking at the pattern, the complexity of your cracks pattern and your spalling pattern and the leakage pattern. That gave you some information because the pattern of a shear crack and a compression crack and the other type of crack is different. And same as the leakage, the sum of leakage shape give you underlying information of how your structure is behaving. So with that index set up, another aspect you should look at is the intercorrelation between different defects. Essentially, the defects, if there's deformation, it can lead you to joint openings and maybe leakage. So the intercorrelation between the defect is also another important aspect to consider for your indexes. The way we try to consider it is we did some of the numerical analysis to see how the spalling and deformation correlates with each other, and how the crack and leakage correlates each other if there's a loading around it. And with that, we will be able to set up some of the correlation matrix. And the technique we used here is called a coupler function. This function was originally proposed by the economic people. They try to see the interlink between two factors, how they affect each other. So we use this function try to identify how each two defects affect each other and to assign the appropriate weights. And based on the amount of data you collected from a tunnel from your region, for example, if you're concerned with the tunnel in Shanghai, you can collect, say, 20 tunnels data, and you will be able to see how the data is clustered. So with that, you can use a classification algorithm, which is a k-means. It's a way of machine learning clustering. So you, based on the clustering method, you will be able to cluster your data into different safety levels. And with that, you will we used the data-driven approach to tell in the region of the tunnel you're concerned with whether in which class it is. So this is a data-driven approach, but typically when we do safety assessment, we usually set some threshold, say if the deformation is larger than 10 millimeters, it's no good, or if there's some cracks or leakage, it's no good. That's still good, but that's more sort of that sort of is not really reflecting what's happening for your region. So this approach, we believe, is sort of a approach which can be fit for different locations based on the data you obtain from your region. You can group them and say, for our case, maybe our case 10 millimeters is acceptable, or 20 millimeters is acceptable. So this classification method becomes important. And this is the one of the case we did in 2019, where there was a gushing problem during the construction. And in the construction process, we had a settlement larger than 60 centimeters. So that's quite an emergency matter. And if we don't treat it in time, it can affect about more than 1 million people. So what we did is basically we implemented the sensor node as I introduced, and we took the reading every minute to see the convergence and the rotation of the structure. Then we also did the inspection, tried to identify what are the cracks and the defects and some of the spalling places. And then we did also some numerical analysis, tried to set up to understand for this about 50-meter section, so what sort of the safety level and the structural safety level. And then we provided essential guidance to allow the on-site maintenance people to do the right decision. So those combining of both inspection and the monitoring can be very important if the emergency happens. And with that all information, our vision is to not only to allow you to present it in the 2D way, also we wanted to put every information in a 3D model. So any inspectors or management level would be able to see my safety status of the tunnel. So with that, we proposed a triangular mesh method. The idea is actually quite simple because we wanted to have not only the texture of your defect, but also the quantified the numbers and some of the information to be printed on the tunnel, on the 3D model. So this model was proposed specific for that task. And then with that model, you will be able to see all the fine details of where the leakage, spalling, cracks, and then you also have a sort of a little inspection table printed on your 3D model, which can be quite handy for the management level to make the right decision. And also you can generate a report automatically. This is typically a report 10 years ago when I go down to the tunnel at midnight, just use a handwriting table. So for nowadays, you can just generate that after your inspection. And with that, we took a step beyond and tried to integrate the model with Unity 3D. It's a typical game engine, which has been widely used in the industry. And integrate of that model in the game engine will give you leverage a really nice 3D model. And you can use either VR or MR glasses to allow the developer to see what is my tunnels doing and how is it good, where the places I should go to treat it. And the table at the bottom can be good to see, okay, if it's green, then this section is not too bad. And if it's go to the orange or red, then I probably should do more with my tunnel. So with that, I think I'll end my talk and I'll just do some little bit of promotion of our center. We assembled this joint research center for resilience infrastructure. We do regular talks. Zili, he's now in Cork in Ireland. I think Brian knows him now. He will join us next month. So we do regular seminars and talks in this center, and those are the founding members of the center. So welcome to watch it out for some of the talks from the website. And we also have a major international conference next year. It's called Zhou Shanghai. We had it before the COVID in 2018, and I would like to welcome you all to Shanghai and try to visit our campus next year. It's in May, end of May next year. With that, I would like to end the talk, and this is our research group. We took the photo about months ago at the cherry blossom in our campus. Thank you.